Yeah, I think something like that. Yeah, I think I got it. What is that? Yeah. I'm going to tell you about it.
Okay, everyone, let's begin. Please ask questions in class. It's much better because usually at the beginning I need to focus and set up the system. And when you ask in class, you get the active learning credits and the whole class would benefit from your questions. Okay, and as I mentioned last time, I'd like to leave the active learning credits for questions that are related to the contents of the course, like math and mechanics, instead of administrative questions. Yes, I mean, I welcome administrative questions, where to find certain file and things like that. Definitely, that's important. I have encouraging a lot of these questions. Please consider. Thank you, David. Continue to ask, but I really would like to hear more questions about math and mechanics. What's the meaning of damping coefficients? Why there's a minus sign in the stiffness matrix and things like that. Okay, and and I remember that Maria. So I'd like to really for the last time, Maria, what
Yes.
team number?
Team 8.
Team 8. And there was one student who asked me how to view the video. Somebody who was sitting here. Yeah, what was your name?
Frank. F-R-A-N-K.
Team 7?
Okay, next time I'll have a list. Actually, from now on, I will take notes on my hard copy. So this way I learn your name as well. So what team number?
Team 7.
Team 7. Sometimes please speak up because it's hard. And so I have team 7 here. And Frank. You're Frank. So from now on, instead of writing here, I will, and this is team 7, I will write on my hard copy and transfer to my daily lecture summary later. And there was a question regarding how to get to this document. Okay, this is one more time. You get to this document through the portal, and you can get to the portal either from Sakai here, or you can just bookmark it, or keep the link somewhere else outside Sakai. It's independent. So there's several ways to get to this document, and let me just click at this portal again. And when you go to the portal, you can really here is the daily lecture summary part 8. So, and also your teammates are also resources that you can rely on for questions like this, and the link to the statement of the problems. And there are other things, for example, the free book and the student solution. And so whenever I update something, I'll mention to you. But this is the way to get to the daily lecture summary, and make sure that you, as I mentioned, look at the daily lecture summary daily, so that you are familiar with the structure. Because if you wait for 2 weeks before doing the report, then you would be overwhelmed by the amount of information. That's one way to do. Another way is create your own document. You can eliminate some of my reminders for me and keep only what you think is necessary for you. Another place that is very useful is the list of topics here. Because the list of topics here serve as like a book index, where if you want to find certain topic, then you can just do a search, right? Do a find command, Control F, type in the topic, then it would lead you to the topic. For example, you can type Control F, and and then eigenvalue problem, eigenvalue. Oh, is it here? Somehow should be able to. Okay, there should be a generalized eigenvalue problem, and if you find some keywords that are missing, just let me know. I'll add in. But there should be the generalized eigenvalue problem or damping or damper, in these. Yes, the eigenvalue. I don't know why it could not find this. It may be depending on certain browser and things like that. You can play around, but this document you should be able to find. Okay. Maybe if I click here, Control F. Yeah. Need to play around with this. Oh, here, fine. Yes, here. And eigenvalue. There's a bunch. And so once you find the keyword, then the document or the lecture notes that has these contains is right here. Click there, and then you bring up the lecture notes. It's very simple. This is you are at the generation where you would be more fluent with technology than I am. So this is like preaching to the choir. Right? Okay, and so please take a few seconds to fill in this survey. This is the survey of on your preferred method to take notes. Okay, you can go to Sakai. You have your smartphone. Please do it now. I sent out several reminders. I think the last time I checked, I had 19 respondents, and the class has 51. So please fill this in, and I'll share with you the results. Okay, you can guess the results. What's the best method. Let's wait until everyone had a chance to fill the survey. For the one who came in late, please fill the survey. Is that Paul? Your name is Paul, right? See, I still remember you. Yes. Please fill in the survey. You'll see that I learned all of your names. And please, mention to your teammates to fill in the survey so we can move forward. Okay. Okay, so let's see. Yeah, so here again, this is the lecture summary, and you see the structure is very clear. The structure is starting with reminders for me to tell the class, and then further details. So I just so there's a lecture summary from Team 8. Team 8 has not picked up the team signature sheet, and then please fill out the survey for note-taking methods. The next thing on the agenda, you see, you can think of this as the agenda of today. Right? So the next thing on the agenda is to show you that Piazza. Several of you already started to use Piazza, but what I noticed is that you use a rather elementary method to write equations. So I'd like to show the class. Okay, for example, when you get to Piazza, for those of you who are not familiar, click at New Post. That allows you to post a new question, a new note, remark, whatever. And then you can select the folder. So this is, I have created various folders from report 1 to report 6, exam, logistics, other. So let me select other. And this is my first post to the class. Okay, I type hello class. But what I want to demonstrate to you is to write equations. Okay, and to write equations, there's this button here, f sub x. That's to write equation. And if you click into that button, you would have an equation editor, right? And you can select the buttons here to type. But if you know the LaTeX code, and it's just like MATLAB or C++, you can type directly, for example, alpha, and notice here, you know, when I type something like the backslash, there are $4 sign, right? 2 starting $sign and ending with $2 signs, and there's a code in between. Keep that in mind because I will demonstrate something later. So I type alpha. So the LaTeX code for alpha, the Greek letter alpha, which is rendered over here, is backslash alpha, right? So if I type backslash alpha equal to backslash beta, right? And you see that you have the equation here, alpha equal beta. Okay, much easier to read. You cannot type in text. And then you click insert. Then you see that the code is inserted into the text box here. And again, once more, the structure is that the code is enclosed in the opening $2 sign and the closing $2 sign, right? In between is the code. And so once you know this, you don't even need to use the equation editor. You type directly. First type $4 sign, right? So that way you don't ever forget the closing $2 sign, right? And then go in the middle and fill out the content, you know, with the LaTeX code. Just like when you code with MATLAB or C++ or whatever language, you want to set up the structure first, if then else, and then you go in and fill in each part, okay? Because if you do if something and then you may forget to close with an if, right? So set up the structure and go in and fill. So here, for example, delta, backslash delta equal to backslash gamma. Okay, so that's the LaTeX code. You can preview the post. So when you preview the post, voila, you know, this is the equation with Greek letters. Alpha equal beta, delta equal gamma. Once you're pleased with that, then you can close the preview. And now I want to send to the class. I select send email notifications immediately as post my notes. All of you would receive my email, you know, with these two equations. Okay, very, very simple. All right, so that's, if you have any questions, you can always pose the questions on Piazza itself, right? Yes.
Explain what the dollar sign is for again.
Explain the dollar sign again.
Yeah.
Okay. You know, LaTeX is called the markup language, right? You want to tell, just like any code, you know, there's certain convention, and you want to tell the LaTeX compiler that, hey, interpret the text in between the double $sign, the opening double $sign, and the closing dollar sign, not as regular text, but as LaTeX code. Okay, so the LaTeX compiler would interpret that the portion in between the double $sign as a LaTeX code, and it would render for you into the image, you know, of the symbols that you wanted. Okay. All right. So this, I think, with your question, that reminds me that there is also a you know, you can explore around. If you click here, yeah, help. You can also get the help, you know, formatting, LaTeX support here, you see, and you see the double $sign here explained again. Okay, so it's a help, it's a manual, okay, but it's very simple. Okay? Just have enclose the LaTeX code in the double $sign, beginning double $sign and ending double $sign. Okay, just practice and work in team. All right, and I just demonstrated that to you. It's recorded in the video. You can watch the video again as well. That's the advantage of videographing all of my lectures. Okay. All right, and with that, I also, as you may have noticed, that in this question on the dampener, not only that, I have provided the answer. In fact, as I mentioned here in my reply, that I have already explained this long before the question was posed. And here I give the link to the video. It's in the third meeting, in meeting 3. Okay. Okay, so you click at the link at the beginning. I explain the physical meaning of the damping force, because Kyle asked what's the physical meaning of the damping or the damper force being proportional to the velocity, right? So I already explained that right here, okay, in meeting 3, very early on. So the question was posed after the meeting, not before. And Anderson add on, with his answer here. Okay, so Piazza is very useful, and all of the questions and answers are archived, okay, and classified. So unlike email, where it may be all over the places and you cannot find later on. So, all right. So that's about Piazza, and I will provide active learning credit depending on my judgment. Okay, if it contributes to the understanding of the class, things like that, So at the beginning I encourage contribution. Later on I begin to discriminate the different types of questions, okay, and replies. All right, so we already addressed Piazza, free books. I have posted here the link that you can download, the free book by Professor Trench, who sent me the PDF, but here I found the link on his site, and also the student solutions manual. Okay, so you can use that, and remember the trade-off is the following. I did say at the beginning that I give this out with the exchange that you would print out my lecture notes in hard copy, right? That was the deal. And you can access these links through the portal, like I have shown to you. That the portal was here. And under the section utility links, I again have these 2 links. Okay. So, and like I said, if you understand my lecture notes, that's more than sufficient. But some student, I understand, requires to read the books. So here, free book, and you also have credit that you can also buy if you wish to. Okay. There's several ways. To have additional references and material to learn. Okay. All right. So, what's the next topic? Yeah. So, one way to review quickly what I did last time is to bring up my handwritten notes in meeting 6. Okay, and I would like to address some questions related to report 1, problems. So meeting 6, and here I probably will talk about 1.3 and 1.6. Meeting 6. So here is my notes for meeting 6 that I annotated after class. So during class I wrote these, and when I went back, I added more comments and reshuffle various parts in the equations, make it clearer. So summary: the dynamic problem is very similar to statics. If you remember the D'Alembert force, and D'Alembert force is minus the inertial force. Okay. Remember the example of accelerating the car, right? If you accelerate in this direction, then your body is pushed back against the car seat, and the force that pushes your body against the car seat, opposing the direction of acceleration, is the D'Alembert force, right? With the minus sign. I just want to mention to you the reason why Michael, the TA, is sitting in the back, because Michael suggested to me a very clever idea. he would rotate, sitting each time with each different team. Okay, so feel free to talk to Michael, convey to Michael your concern, whatever you wish to convey to me, but may not feel comfortable. Then talk to Michael, and Michael will let me know. So he'll rotate and sit with different teams on different lectures. All right. So with this, I would like to bring up report 1 problems again, and remind you that I have asked Michael to put in the resources, right? So everyone, I hope, knows how to get to the resource folders on Sakai. You over here, if you get to resources, then the best solutions and best reports from last semesters are all here for self-study. And as I mentioned, try to do it without looking at these. And if you get stuck, then you can look at the best solutions and best reports just to get unstuck and move forward, enough to get unstuck to move forward. But that's a tool that you can have in addition to asking me questions, asking Michael, right? So that is something that you have to, for self-study, and also to emulate the best solutions and best reports. Okay, report. Yeah, I have also reduced the number of problems that you need to report already. So you see that it's less work than last semester, and also you are provided with the help, right? With the best solution and best report. So there's a lot of help already. There's less of a reason to be confused. But if you are still having questions, please bring up on Piazza, bring up in class, talk to me, talk to Michael, okay, email. So, all right. So 1.3. The reason that I'd like to go through this with you is because this is not the easy problem. The easy problem are the things that I ask you to, to do a self-study. Yeah, 1.3, the 1.2 is the easier one, where you have spring, mass, and damper in series, and both ends are fixed. Okay, and the other are the parallel, spring and damper in parallel, and that's what we did in class as well. So 1.1 is real easy. 1.2, sorry, I say real easy, but if it's not easy, then it's not easy. So please ask questions. And say easier is probably the right word to say. So I'd like to address this because I did mention in class that how you address the case where the spring and the damper are parallel is different from the case where the spring and the damper are in series. Okay, let's review here. Maybe can someone quickly say the differences and the similarities between the two systems and get active learning credit. You look unfamiliar. I know you already contributed, so let's bring in new friends here. What is your name?
Jason.
Team 8, and your name? Jason. Okay. So you see, this is how I will mark down from now on. And this is meeting 8. Okay, Jason, could you quickly remind the class?
In series, the forces are equal, and in parallel is the distances are equal.
In series,
Forces are equal.
the forces are equal, and in parallel,
The distances are equal.
the distance or displacement.
Yeah,
Displacements are equal. All right. I think I may have a note. Yeah, right here. So this is in series. When you do free body diagram, you see that the internal forces are equal. But what is tricky compared to the case in parallel is that you need to add the displacement to get the total displacement. So let's illustrate that by the solution of problem R1.3, and the solution is given in section 1, okay, already. And all you need is just to draw free body diagrams, retrace the argument, the derivation, and that would be it. Let's see. I would have. Bear with me a second. I thought that I have the file here, but it can also be clicked. If you click at the link, you can download. But I'd like to use the PDF viewer so that it's easier to look at. And by the way, I did give you the printout, right? The printout of section 1. So you have the hard copy. Okay, so let me. So this is section 1 here. Okay. And so if you go to section 1. And let me do this so that you can see where the page would be, and you have the hard copy, you can follow. So here, so right here. Okay, this is the page 1-4, meaning section 1, page 4. And let's zoom in. So if you focus your attention to this figure, then you see that this is a system where you have a spring followed by a damper and a mass in series with one end fixed. The spring end and the mass end, the end where there's a mass is free. And there's only the horizontal motion. If you have a problem visualizing the horizontal motion, you can think that the mass is on roller. So there's no transversal motion. Okay? It's only going this way. Okay, by roller, I think you can draw in your notes that the mass sits on the roller like this, and the damper also is supported by the roller. Everything is moving only in the horizontal direction. Okay. So here is an example where the displacement of the mass here denoted by y, because in the book by Krasik, the dependent variable is denoted by y. The independent variable, sometimes x, sometimes t, and here t is mnemonic for time, right? So this is the displacement of the mass, and this is the force applied on the mass. Okay, and so you can think of this as the total displacement. You have to add the displacement in the spring to the displacement in the damper to get the total displacement. Right? This is different from the case where the spring and the damper are in parallel arrangement. When it's in parallel, the displacement is the same, but you add the forces. Okay, so that's the fundamental difference that Jason of Team 8 just reminded the class. All right, so how do we go about to do this? So this is the kinematics here, where you see that, okay, you write the total displacement as a sum of the displacement of the spring plus the displacement in the damper, right? And then kinetics. Kinetics is essentially relationship among forces. Kinematic is relationship among the displacements. And so this equation here, I'd like you to derive. How do you derive this equation? Could someone, based on previous lectures, tell the class how would you come up with this equation? this is based on previous lectures, so I'd like to bring in someone new, and I know, okay, yes, sorry, I already, next time please faster, I don't care about whether it's right or wrong, okay, this is, just react quickly, yes, please.
You do the sum of the forces from the free body diagram.
Free body diagram, yeah, so you want to use the Euler-Cut principle to decompose into free body diagram. What is your name? What's team number?
Team 2, my name is Colton.
Team 2, and the name is Colton?
Colton?
Colton, yes. Yeah, so free body diagram, essentially, okay, let me, yeah, you see that if you focus on this part here, you see that this part, it was what Jason mentioned, the forces are equal, and this equation, the top equation, this one, is coming from the free body diagram of the mass. Okay. So it goes as follows. So let me use my notes here so that you have something left. Okay, so free body diagram, you can do can draw something like this. You have the spring. This is after we perform the Euler-Cut already. So I directly, perform the Euler-Cut, meaning you cut everything up, remove the support, isolate all of the components, and this will be the mass, right? Okay. Now, remember this is, so first you want to report the displacement and the applied force, and note that the displacement is denoted by y in this problem as a function of time t, and then you also have the applied force, right? And let's use the same notation so that here lowercase f, this is the mass m, and because you cut off, there's some, we can have a portion of the connector, and so you need to have an internal force. Let's denote that by F sub I, right? And don't forget the D'Alembert force, because remember the assumed positive displacement is in the positive x direction, so the D'Alembert force has to be opposite the direction of motion, and that's like this. You can draw down here or up here where there's more space. Let me draw like this. So this would be m y double dot or double prime. So sometimes because when I type, the prime is shorter to right than the dot. Okay, it's just a LaTeX code. So for the damper, you have the damper force. You can maybe let me leave some space. Right, the damper force here F sub c, F sub c, and then you have you can say that this is F sub k and F sub k. Okay. So everything is in the positive direction. To have the balance, let me put the minus here, because the sum of forces for each component has to be, when you sum the forces, it should be 0. So the sum of forces, for example, for the spring minus Fk plus Fk would be equal to 0. Okay. And this picture is similar to the picture that you would see in statics. So let me just put a note here that this is the same as if I remove this minus sign, then you just reverse the direction, right? So that's the same thing. Okay, the two way to write is entirely equivalent, meaning the sum of forces has to be 0. But this way is how the finite element method is formulated. Everything is assumed to be in the force equivalent. Okay. So from the free body diagram here, you see when you put all the components together, the three forces must be equal, right? Meaning that F sub k must be equal to F sub c, must be equal to F sub I. Okay, that's the that is just by action and reaction. All right, and for the three components in series.
And then when they're in parallel, it's minus?
When it's in parallel, you add the forces, but the displacement is equal. Here, you need to add the displacement, but the forces are equal. Okay. So you add the displacement means that you write the following: y, which is the total displacement of the mass, equal to the displacement in the spring plus the displacement in the damper. That's when you have three components in series. Okay, so let's. So essentially, that's it. So if you look at the equilibrium of the mass, right? If you look at the equilibrium of the mass, you sum the forces equal to 0 of the mass on the mass, right? You have minus my double prime minus F sub I, the internal force, right? Equal to plus F of t, right? Actually, you can also put the time here, because the internal force is also a function of time. Okay? Everything is function of time, including y. And this is equal to 0. Right? And so that's it. You have derived, or I have derived for you, this expression. You see here. My double prime plus the internal force on the mass equal to the applied force, Ft, through free body diagram. The only difference between dynamic and statics is the D'Alembert force. That's all that is. Otherwise, the rest is exactly the same as statics. Does it make sense to everyone? Right, let's bring this up once more here. My notes. Okay, this is just by looking at the equilibrium of this mass here. Right, you have sum of forces equal to 0, so the D'Alembert force minus My double prime, the internal force minus F sub I plus the applied force F equals 0. And
Is this only for equilibrium?
sorry?
Is this only for equilibrium? Is this only for equilibrium?
Could you repeat, please?
Is this situation only for equilibrium?
Well, dynamic equilibrium, not static equilibrium. Yeah, because you have the inertial force. Right? So if you move these two terms with the negative sign, or to the right, and then swap the two sides, right? So if you move these two to the right hand side, you have My double prime plus F sub y equal to F. And then you just rewrite the two. Just swap the two sides. Okay. Then you get this this formula here. Right. This one. And then f sub I is equal to f sub k equal to f sub c. And since f sub k, the spring force is a function of the displacement in the spring, and the damper force is a function of the velocity in the damper, then you can bring in the spring displacement and the damper velocity into the equation. But that's getting, you know, as I wrote here, f sub k is k times y sub k, and f sub c is c times y prime sub c, and y prime sub c is the velocity of the damper displacement. Up to here, is it any further questions? Why do I move my prime plus f sub y to the left hand side, and on the right hand side there's f? Why? Yes. What team number? Whenever, please say the team number first and then your name, and I can follow. Team?
Team 6.
Can you say louder?
Mohammed, Team 6.
Team 6, Mohammed. Okay, let's see. Yes, Mohammed, go ahead. Why did I swap the two sides?
So you're balancing out the forces on the mass.
So what?
You're balancing out the forces on the mass, right? So you have the overall force going that way, and that's the inertial force.
Okay, let me repeat the question, you know. You see from this derivation here, maybe let me write over here. Okay, what I said is the following. If I, from this equation here, right, this equal to 0, okay, what I'm saying is that let me move these two terms to the right hand side. Okay, and then the minus becomes plus, right? Okay, that is just a direct rearrangement of the terms. There's no mystery. And then I said, okay, let me swap the two sides, meaning let's move the right hand side to the left. Oh no, I'd like to leave this equation here so you can follow in my notes, and that's why this is the very powerful way to do. I move the right hand side to the left and the left hand side to the right. That's all. I just swap the two sides. And when I swap the two sides, you get the equation, at least in terms of the internal force. You know, there's inertial force, internal force, and applied force. And the reason that I do this is because you want to have the unknown on the left, because this, you know, later on you replace the internal force in terms of the displacement in the spring and so on and so forth. And then this is known because this is the applied force, usually is prescribed and therefore known. What is known is on the right, what is unknown is on the left. That's the reason. And that's why you see written here in these notes. Okay? And note that I also have a video for this lecture notes. So if you need to look at the video, you can look at it. But let me move forward. So once you do that, the next step is to bring in the displacement, right? You want to replace F sub I, the internal force at the mass, either in terms of the displacement of the spring or the displacement in the damper. Here in this formulation, I choose to work with the displacement in the spring, okay, y sub k. And you see that this is the relation here. You have the force, internal force on the mass equal to spring force equal to damper force. Spring force is proportional to spring displacement y sub k. Damper force is proportional to damper velocity yc prime. And because you have y plus yk is equal to yc, you can take the derivative, second derivative, and you also have the same relationship among the accelerations. Total acceleration equal to spring acceleration plus damper acceleration, right? You can translate mathematical equation into prose. That's very important. And so because f sub k equal to f sub c due to free body diagram, you see that you have a relationship between the spring displacement and the damper velocity. So, it takes longer than I thought, but I think it would be helpful. And then all you need here is once you know the relationship between yk and the velocity, you can express yc prime in terms of yk, right? And so you can express the acceleration completely in terms of yk, okay, the displacement in the spring. So you see that the total acceleration is equal to the acceleration in the spring plus a term that is proportional to the velocity of the spring, okay, and that was due to the damper. And then you would arrive at this equation, which is not as simple as in the case where you have the two ends that are fixed. So here you have mass times the acceleration of the spring plus a damping force term, but now the damping coefficient is actually k over c, okay? K over c, not just c. And multiplied by the mass, so m times k divided by c times the velocity in the spring. And then you have the spring force equal to the applied force. That's why the case where you have the spring, the damper, and the mass in series with the end of the spring fixed and the mass free is more complex than the case where in the problems that I didn't ask you to turn in. But here is a complete explanation. All you need is just to rewrite what I explained. Okay, any further questions on this part? And you have also the best solutions to help out. All right, I wish that I could go further. So let's do a lecture summary. You can write any questions that you may have further in that. Oh, if you need extension for the report, just let me know. Okay? I can extend further, but
First time
up to a limit.
you go back and you do round two.
The deadline.
Oh, yeah.
So that was
Do you have officers? I know they're on. Do you have officers today?
yeah, 'cause it was like I remember the report from that
But we will work with the TA to have also TA.
I don't know what the rules are. I think the rule document
Yeah, we have done it.
All right, here's
Well, then you guys help us.
Yeah, that's our email.
oh, put it on the Dropbox.
Remember, there's also the best solution to best result.
Problem solved.
Whenever I say no.
Yeah, 5.
Whatever I say no.